The third example in the flow in a duct that we will be considering now is flow with heating or cooling. So, these are the three common factors that can produce continuous changes in a flow in a duct, that is the variation in area, effect of wall friction and energy effects such as external heating or cooling, which includes combustion, condensation and so on. Now, we have already considered flow with area variation without friction and heat exchange. Then we have considered flow with friction without area variation and heat exchange, and now we will consider flow with heating or cooling, but no area variation and no friction, and of course, as before the duct is uniform. So, flow with heating or cooling is the topic of our discussion today, and we will assume uniform duct no friction. And of course, as before we will be using one dimensional flow, that is at any cross section we are considering only the average properties. Now, usually the mechanism of heating or cooling will be associated with many other effects. They may produce friction, and also when there is combustion or condensation involved, there is a possibility of chemical reaction and change in species or change in phase also, and consequently heating without these additional effects in real case is usually not possible. However, in this idealized case we will consider the heating is such that it produce no changes in composition or phase and it produces no frictional effect. The heating in this case produces only a change in T 0. So, these flows are also can be considered a simple T 0 change. So, we are considering an idealized case. No change in composition, no change in composition of the gas, no change in phase, and only change in T 0 due to heating or cooling. Now, these flows are commonly called as Rayleigh flows. Now, with constant area and no friction, the momentum equation is with uniform cross section and no friction, the momentum equation is simply gives us P plus rho u square equal to constant, and as you have defined earlier that P plus rho u square is called the impulse per unit area, that is impulse per unit area is constant. Now, continuity of course rho u, that is mass flow rate per unit area, is constant, and if we combine these two, this gives us P plus g square by rho equal to F by A equal to constant. So, for a fixed mass flow and fixed impulse, this is a unique relationship between pressure and density, and it can be plotted in the PV diagram. So, for fixed F and G, unique relation between P and rho. Can be represented in P 1 by rho or P V, that is the specific volume PV diagram, and of course, in P 1 by rho the diagram is basically a straight line, and these lines are called Rayleigh line. So, those lines are line representing the relation is called Rayleigh line. Of course, we will have separate Rayleigh line for separate values of f and g, that is the separate values of impulse function and mass flow rate. Now, for a pure substance, this P and rho can also be expressed as a function of H and S, and they can be converted to a relationship between H and S. Now, P is a function of enthalpy and entropy, and similarly rho is also a function of enthalpy and entropy. So, the line can be represented in the HS diagram. And as you have seen in case of Fano curves, we can see these Rayleigh lines or Rayleigh curves have also general form. So, like Fano curves, Rayleigh curves also have a general form for all substances. Now, let us see this. So, this is the general form of Rayleigh curve. Now, for continuous changes in duct, as we mentioned earlier, that there are most commonly these three factors: heating or cooling of the flow, or wall friction, or change in area, which in essence is isentropic flow. So, all can be represented here. This so this is that let us say that the isentropic change So, these are the three different paths that the fluid will follow in case of the respective change. For an isothermal change, for an isentropic process or isentropic change, as it happens in a duct of varying area without heat addition and friction, the state of the fluid will always lie on this path. In case of uniform adiabatic flow with friction in a duct, the flow states will follow this Fano curve, and when there is heat addition, but no change in area or no friction, the process will follow this Rayleigh curve. Now, as we know that in heating the entropy changes, and while in cooling the entropy decreases. So, the path that the system will follow, that if cooling is allowed, then this will be the system direction, and if heating is done, then the system will follow this path. That this is the maximum entropy for the given value of f and g, that is the given value of the impulse function and the mass flow rate. So, you see that in case of heating, the fluid takes the path to reach the maximum entropy condition, and while cooling it goes away from the maximum entropy condition. This is the constant pressure line through the maximum entropy point, and let us say this is the similarly you can have constant pressure line at this point shown as P 1. Now, let us coming back to the relation that we already had, that P plus g square by rho equal to constant, and this implies dp d rho equal to g square by rho square. Now, we know that dp d rho, if evaluated isentropically, represents speed of sound. So, dp d rho evaluated isentropically equal to a square, or rather that this represents the speed of sound only in the special circumstances when a change in pressure, a very small change in pressure causes a very small change in density, such that there is no change in entropy. Now, we can see that this situation is fulfilled at the point of maximum entropy. So, that is dp d rho represent speed of sound only for the special condition when an infinitesimal variation in pressure changes the density infinitesimally in such a way that there is no change in entropy. And from this figure we can see that this happens at the point of maximum entropy. So, in the Rayleigh curve, is evaluated isentropically at S max point. So, this implies that S max point represent sonic state or state of m equal to 1. So, in the Rayleigh process or simple T 0 change process, the point of maximum entropy represents the sonic state or state of Mach 1. Now, if we consider the state at point 1, beginning the state at point 1, from here Mach unity can be reached in several ways. They might be isentropically, they might be adiabatically at constant area, they might be at with changing friction, they might be due to with heat addition, and were only for the simple heating process that maximum entropy point on the Rayleigh curve will represent the sonic condition, or the sonic condition in the Rayleigh curve will only be represented by that maximum entropy point. Now, the branch of the Rayleigh curve, we once again come back to the Rayleigh curve. This is subsonic part, this is supersonic part, and we can see that a subsonic flow, if heated, tends towards sonic case. Similarly, a supersonic flow when heated again tends towards the sonic state. Similarly, in case of subsonic flow, if cooling is allowed, the Mach number decreases while it increases for supersonic flow. should from this you can say that a subsonic flow accelerate in heating while it decelerates in cooling. And opposite happens when the flow is supersonic. That is, a supersonic flow will decelerate if it is heated and it will accelerate if it is cooled. So, heating causes the Mach numbers tends towards unity and cooling causes the Mach number move away from unity. So, heating causes Mach number to approach unity and cooling causes Mach number to change away from unity. So, the heat addition or the amount of heat that can be added to a flow either subsonic or supersonic such that the maximum heat that can be added to a subsonic or supersonic flow can be such that the Mach number become unity. The amount of heat cannot be greater than that for which the Mach number that leaves the duct is more than 1 or different from 1. Now, if the addition is if the heat added is more than that heat or the maximum amount of heat that is required to take the Mach number to unity, then there will be the flow will be choked and the Mach number at the exit will remain at unity, but there will be change in the inflow condition. And this choking by heating is called as thermal choking. So, we have a choking process here. That is, that if we have a given duct and we have a fixed amount of mass flow, specified amount of mass flow and impulse function, then there is a maximum amount of heat that can be added to the flow such that at the exit the flow Mach number becomes unity. Now, once this flow Mach number reaches unity, if more heat is added, then additional mass flow is not possible, no more change in Mach number, the Mach number at the exit still remain unity. However, the inlet condition changes and the mass flow rate decreases. So, what we say that the amount of maximum mass flow rate for a given duct depends on the amount of heating for which the Mach number will become unity at the exit, and this is the condition of choking, that is the maximum amount of heat, maximum amount of mass flow that can be allowed when heat is added. And since in this case choking is taking place due to heating, it is called as thermal choking. Now, let us try to estimate or evaluate all the parameters considering the gas to be perfect. So, we will call the estimation of all parameters. Estimation of the flow parameters for perfect gas. We have from mass conservation one relation. From momentum equation we have P1 minus P2 equal to mass flow rate per unit area divided by multiplied by U2 minus U1 . And to be precise, that m dot is basically rho u. Now, we know now rho u square is as you have seen is equal to gamma p m square. So, the momentum equation can be written as 1 plus gamma m 1 square by 1 plus gamma m 2 square. The equation of state can also be written as equation of state P 2 by P 1 equal to rho 2 by rho 1 into T 2 by T 1, and or we have T 2 by T 1 equal to P 2 by P 1 into rho 1 by rho 2 that equal to P 2 by P 1 into U 2 by U 1. We also have from the definition of Mach number for a perfect gas, and using perfect gas relationship, this becomes U 2 by U 1 into root over T 1 by T 2. Using perfect gas relation for speed of sound, the impulse function relation can be written as f 2 by f 1 equal to P 2 by P 1 into 1 plus gamma m 2 square by 1 plus gamma m 1 square, and since f 2 by f 1 as you can see, this P 2 by P 1 using the earlier relation P 2 by P 1 is this. So, you can write P 2 by P 1, already we have 1 plus gamma m 1 square by 1 plus gamma m 2 square to 1 plus gamma m 2 square by 1 plus gamma m 1 square equal to 1, which of course, we have seen in the beginning that the impulse function is constant for flow in a uniform area duct without friction. Now, from isentropic relation, stagnation pressure relation, to the power gamma by gamma minus 1 and the change in entropy delta S by C p, that is S 2 minus S 1 by C p can be written as log T 2 by T 1 divided by P 2 by P 1 to the power gamma by gamma minus 1. The energy equation can now be written as amount of heat added is C p into T 2 minus T 1 plus U 2 square minus U 1 square by 2, and this is C p into T 0 2 minus T 0 1. So, this is the form of the energy equation. Now, using the definition of stagnation temperature, T 0 2 by T 0 1 is simply T 2 into 1 plus gamma minus 1 by 2 m square by T 1 into 1 plus gamma minus 1 by 2 m square. Now, this if we substitute this relation, in particular the result that we have obtained from the momentum equation and from equation of state and continuity, if we substitute into the equation of state, what we get is now we already have T 2 by T 1 equal to P 2 by P 1 into U 2 by U 1, and for P 2 by P 1 we have 1 plus gamma m 1 square by 1 plus gamma m 2 square into U 2 by U 1. Also, we have U 2 by U 1 as m2 by m1 into root of T2 by T1, and this gives T2 by Q1 equal to now this temperature ratio can be substituted into the stagnation temperature ratio to find the stagnation temperature ratio in terms of Mach numbers alone, and this gives us T02 by T01 as m2 square by m1 square into 1 plus gamma m1 square 1 plus gamma m2 square whole square into 1 plus gamma minus 1 by 2 m2 square divided by 1 plus gamma minus 1 by 2 m1 square. Similarly, other relations for P2 by P1 and rho 2 by rho 1 and U2 by U1 can be obtained for other in terms of Mach number. Similarly, P02 by P01 U2 by U1 rho 2 by rho 1 can be expressed in terms of M1 and M2. Now, it is quite useful or convenient to set one of these state, that is either the condition 1 or condition 2 as the sonic condition, and convenient to set one of the sections as the section where m equal to 1, and this gives us then T star is gamma plus 1 square into m square divided by 1 plus gamma m square square. P by P star equal to gamma plus 1 by 1 plus gamma m square U by U star, that is of course the inverse for density ratio rho star by rho, that is gamma plus 1 into m square by 1 plus gamma m square the stagnation pressure ratio between two stations. One station is where Mach number is 1, the other station and any other station where Mach number is m. The stagnation pressure ratio becomes gamma plus 1 by 1 plus gamma m square into 2 into 1 plus gamma minus 1 by 2 m square divided by gamma plus 1 whole to the power gamma by gamma minus 1. And this gives the entropy change. Essentially, in this form only, in the Rayleigh flow tables that are usually available in all books, all textbooks. In this form only all the parameters are given, that is, parameters are expressed as a ratio between the properties at two section, in which at Mach number at one of the section is unity and the other section is the value m, and the tables are available for different values of m. And once the ratio of these two properties are obtained, so you can say these are the ratio of the properties between two sections, ratio of properties between two section where m equal to 1 at one section and m equal to m at the other. And as you and once ratio in these form are known, the ratio between any two stations where Mach numbers are m1 and m2. Say we can find T02 by T01 as an example, as T0 by T0 star corresponding to Mach 2 and T0 by T0 star and similarly for other ratios. That is T02 by T01, where T02 is the stagnation temperature at station 2, where Mach number is M2, and T01 is the station 1, where Mach number is M1, and that ratio can simply be obtained by T0 by T0 star evaluated at Mach 2. That is, in this relation, if M is used as M2, that is what T0 by T0 star at M2 and T0 by T0 star evaluated at M1. Similarly, for other relations also, for other ratios also same relation holds, similar relation holds, and all the properties can be obtained and solution be completed. So, to summarize, we have considered now in today's discussion flow in a uniform duct with simple T0 change. That is, we have considered heating and cooling in such a way that this heating and cooling simply changes the T0 of the flowing gas. It does not add friction, it does not change the property, or it does not change the composition and phase. Of course, it can be thought of that if there is a change in composition, but we can an equivalent process is considered in which the composition change or other effects of composition changes are not there, only the change in T0 happens. And for these flows we have seen that if the flow is subsonic or supersonic, when it is heated it tends towards Mach unity. However, if it is cooling, then the Mach number flow Mach number always moves away from unity. That is, a supersonic flow in cooling become more supersonic or its Mach number increases, while for subsonic flow it is decelerate, its Mach number decreases. In case of a heating, both subsonic and supersonic flow approaches towards the sonic condition or Mach unity. Also, we have seen that for a given mass flow rate, there is a the exit Mach number for a duct can be 1, and if more heat is added, the mass flow rate only adjusted, so that the Mach number at the exit remain unity, or rather there is a for a given duct there is an maximum amount of heat that can be added without changing the initial conditions, and this is called thermal choking. And then considering perfect gas, we have derived the relationship that can be used to find the properties between different sections, and as you have seen that like isentropic flow, Fano flow, normal shock and oblique shock flow, there are flow tables for this Rayleigh flow or simple T0 change type of flow, where ratios are usually expressed in the ratio between two stations, in which at one station Mach number is unity, the other station is a general station. And from these ratios also, considering two ratios at two different Mach number, we can find the desired property also.